know how to do machine learning. It's like a different universe generally. The machine learning, I would get it close to like statisticians and like the sort of data analysts, and like I would
Econometrics and
put,
stuff.
yeah, on even econometrics. Like I would put it closer to that realm rather than like software engineering and stuff like that.
That makes sense.
That's my idea though. Yeah.
All right, let's do it. Hey,
All right.
Matt, you're there, right? Oh, hey, Matt. Yeah, yeah, we were wondering where you are.
Okay. Where were we? So I think we established to a point where, let me large this up. Okay. Well, we established to the point of how that neural network system works. Uh, in each batch, it will go on a start on a like a space within the error space, and it will calculate the gradient, and depending on where the gradient is pointing, it will take a step towards reducing the loss function, and it will conduct this over and over again, and it will take steps towards that so that it can find the best sort of minimum loss point that it can. And these steps is important, like the steps that you take. Imagine you calculate a gradient, you're like, okay, I need to go that way, this is the way to go. How big of a step you take is important, and that's what we call a learning rate. We talked about this a little bit whenever Valentino asked this question. The learning rate, generally the idea is that like how big of a trust do you want to put in the like the gradient descent that you're calculating in your batch sample. If you want to like wind up taking too big of a step, you might miss your optimum global minimum. If your step is too small, you might just come here and get stuck here and never find your optimum minimum, right? And generally, this is how a neural network works. And we will get it a little bit deeper in a minute. And also have in mind the difference between the classification and regression here. The only difference whenever you're like coding it, implementing it at least, is that the last layer you're using in classification must have a softmax activation function to give you out probabilities rather than values. This is very important, but I'll repeat this over and over again because of like when I learned to do regression with machine learning, I had this whole issue with this thing, and I realized how simple it was to just convert everything. All right. Let's go back. There we go. All right. So we talked a little bit about these learning rates, right? We want to find the best learning rate. We want to move towards a degree where we can find the optimum minimum. But how do you define this sort of learning rate? How big of a step do you want to take? One way of going at it is trial and error, which is like something very popular in the machine learning realm. But fortunately, a bunch of smart people got in a room and like created the libraries that we were talking about with Brian. Is that they created a sort of a dynamic optimizer functions where you could just define your optimizer by giving it one of these libraries, and they each work differently, and I'm not going to go into it of how they work. They're each suitable for a different type of problem, but these are like if you give an optimizer to your neural network, it will adjust your learning rates depending on what sort of batch it is seeing at the moment. Now, all that heavy stuff, the coding for it, like a 3-layer neural network, is as simple as what you see on my screen. It's like implementing is super easy. We use a software solution called TensorFlow and Keras to code in Python and create this neural network. What we're looking to create here in this code is to create an input layer where we have 6 entries. If we go back to this picture, let's go. Okay. Imagine we have 6 of these X's. We want to have 8 of these hidden layers, and we want to have 4 outputs, I believe. This is the thing we want to design in that block of code. And this is what we're looking to code there. And we can see the model here. And the easy enough, you can just create a model by writing this piece of code, model sequential, and you will create a dense layer. Remember, dense layer is the one where every sort of cell is connected to one another. It doesn't have to be that way, but that's like it's this whole sort of piece of literature where they like talk about which design is suitable for what problem. You design a layer, you tell it it's a dense layer, you say it must have 8 cells, you will give it an activation function, and you will tell it the input dimension, which is our input space, is 6. And that's your hidden layer, basically. You also want an output layer, and your output dimension is 4. You get, again, it's a dense layer, and you get it and you give it a softmax because this is a classification problem. Whenever you're doing a classification problems with neural networks, always use softmax. This will give you an output of probabilities. It will give you a probability ranging from 0 to 1 of how likely it is to be that class for a certain x. As we saw before, we also define an optimizer so it can, adjust our learning rate through the learning by itself. After doing the design part, we compile our model. We tell it to put this optimizer in the optimizer category. We define a loss function, which I define categorical cross entropy. Again, if you don't know what any of these are, that is fine. If you just put like Google TensorFlow loss functions, it will give you like 8 things, and there are codes on all of them, examples of them. You can just see like how each of these like things work. And you provide the metrics. And after that, exactly like SVM, you just like fit the X to the Y. But this time you give it an epoch number, which we discussed before, and you also give it a batch size. We'll talk about this piece of code in a little bit whenever we go into our example. So that was general idea behind neural networks. Have in mind, like this is the hottest sort of algorithm in machine learning today, maybe next to reinforcement learning very recently. So like all of these things that we're talking about like get considerably deeper, and they vary depending on what problem you apply to. And this is just a general perspective, and the deeper your neural nets are, the more complex each of these relations are going to be. With that in mind, any questions on neural networks? I can go back on any slide if you want. Like Hugh gave me the time, I have the authority now. Any questions?
Where would I put that code? Where would I exactly put that? I'm not entirely sure where I would put it.
That's for your references. We'll go over how to put the coding in. Imagine like this is a Python.
That code would be used. This is the structure which will be used for any particular function you want to do.
Yeah.
And Faraz will give you an example of how these things will be used for a particular function.
That's true. Like this is for your library. Whenever like 3 months from now, you're like, okay, how did I design a dense layer? You come back to these slides and you just copy this and paste it, right? But the idea is at a point in time, if you have your X and Y defined, this will just train your neural network model, this script. And all the like features you need to deal with, the activations, the number of inputs. I just put them in there for your future references. We're gonna go through a sort of a more relatable code in a minute.
Very simple one example.
Yeah. Any questions? Okay. All right, this is the part we actually talked about in the beginning of the class, the evaluation of the model. And I assume we're all familiar with accuracy. We're familiar with like R-square and absolute error when we use it with regression models. The general idea of accuracy is like you want to be able to find the true positives and true negatives of your model, do a summation of that and divide it by your entire space, right? The true positive, true negatives, false negatives. Now, depending on the problem you want to deal with, you might want some other measures as well. Like imagine if you have a problem and you care a lot more about classifying one of the classes compared to the other one. You don't really care about mistakes in the other class. You just want to classify one of the classes correctly. For example, that's when you might want to use precision. And precision is like true positive divided by true positive plus false positive. right? That will give you an idea in that feature. Okay, how good am I in predicting true positives? And you also have recall. Precision is a little bit more intuitive, but you have like a bunch of different sort of measures. These are the ones for like measuring the classification problems. As for the regression problems, I believe you should all be familiar with like the R square, which sort of calculates the one minus the unexplained variation divided by the total variation. Generally, the higher it is, the better. That means the more your model is explaining. You can also drive the absolute error or any other loss function and calculate it for your set. And have in mind, you want to calculate these evaluation metrics for both your train sample and test sample. You will get a lot of insights by doing that. You want something that generally works good. Now, we sort of touched in this too, but like imagine we train a model, we train 3 model on a problem, and we have the following evaluation metrics of it. Which of these models would you choose to deploy in the real world?
B,
That is true. Why?
because its test accuracy is the highest. Or, yeah, the test accuracy is the highest.
That is true. Very good. So like if you look at C here, this is obviously overfitting. It can only like predict the train accuracy. This is just modeling noise at this point. This has 0 value. If you look at A here, this A is like has similar performance, but if we train it more, we might be able to get an overall better accuracy. Where you want to be at is like generally having similar accuracy between both test and training samples. When I say accuracy, I mean all the other like measurements, R squared, whatever you're measuring, right? And you want to have similar ones, and you want to train it to a point where like it doesn't make sense to train, because this is too early. You can improve this model because they're exactly the same, but this makes sense. And the general idea is like, do not overfit and do not underfit. As we said before, like we don't want to miss out on the stuff that we could have predicted. And that would make sense a lot from an investment perspective. We want to be able to grasp whatever opportunity we have, but we also don't want to just model noise that doesn't make any sense in the real world. And the there's a lot of time spent in this thing, finding this sweet spot where you're happy with your model, and that is like a whole sort of main part of this, like doing a machine learning problem. If I think I mentioned there was a Jane Street trade competition a while back. Like the initial results came in we were able to like model a bunch of stuff, and we would submit it on a particular sample, and the top scores on those samples were like 11,000, and it was calculated with a function, like with a utility function, but that doesn't matter. Imagine the top score was 11,000 in the like closing day of the competition. Now they're testing those models on like new real world market data. They're plugging in our models into the market, and now the top score is 5,000. What that means is all the people who had the high score before the competition closed, they were all overfitting their data to the sample. None of them made any sense in the real world. And you want to stay away from that as much as possible. Again, we talked about this a little bit previously, but the general idea is that you want to, because theoretically speaking, we talked about this, you can always reduce the error with more training. You can always reduce it. But you want to reduce that to a point where your model doesn't become biased on your training. It doesn't overfit here, because at some point it's just like whatever is fitting here is just nonsense. It has no rational value behind it. And you want to stop at a point where your validation score, whenever I say validation test, like they're the same thing. The better way is to like you do it on a test, then you do it on a optimize on validation, and then you do it on a test. So like think of it as having 2 test samples to like make everything foolproof. But generally, like whenever your test sample starts to diverge from your training sample, that's a good idea to stop. And whenever this gap is getting larger and larger, you're not doing the right thing. You're just like overfitting. And we have like ways to battle this, like with generalization, as we saw with SVM. If we sort of reduce to C, we were going to get more generalized. We would be more unlikely to overfit. And we also have something in neural networks called a dropout rate. I'm not going to get into it much, but you can generally define a dropout rate. And what that dropout rate does is like it will randomly remove some of those cells during different epochs. And to make everything more generalized, it would randomly remove a bunch of different data and be like, okay, this didn't exist. How would you predict now? So what this does is like it's trying to not let the model fall in a pitfall of that, like that one cell where it's just like creating nonsense there. But intuitively, these are good things. You would always want to use some sort of a dropout rate to improve your model generally, especially if you're working with larger data sets and larger networks. Now, one more concept before we get into the actual coding, and that's knowing your data. Any questions, by the way, on the last 2-3 slides? No? Okay, good. So the whole, as I mentioned before, the whole like purpose of this like thing is you need to know your data, and your model is only as good as your data. Because if you're giving it like garbage in, garbage out, if you're giving it bad data, like it's not going to be able to find anything. And you need to understand your data. And whenever like in your homework or any other problem you're going to deal with, is that like the first thing you have to do is to like understand your data, draw charts, draw like get statistics on it, draw diagrams, look at it, see if you have any missing values. If you have missing values, how are you going to handle it? My general recommendation is to replace it with a median, right? If you have missing values. But you might have a problem that it might be better to like completely eliminate the missing values, because you cannot have the null values whenever you're training the model, because the model will not be able to recognize what that null is. And if you put random variables there, your model is just going to not recognize it at all. You also need to like handle non-numerical data. The machine does not understand red, green, blue. These do not make sense. So you need to convert these into numerical values. And we have two ways of doing it. I will talk a little bit about that in our example. But if we're dealing with something like large, small, medium, you can just go with like 0, 1, 2. That makes sense intuitively, because they make a sort of irrational sense. But if you have like red and green, you might want to like turn that into a what we call a one-hot encoding. Whenever you convert that into two columns, instead of like color red, green, you would convert that into red, blue. Okay, if it's blue, 0. If it's not blue, 0. If it's blue, 1. And the same thing for the reds. You will convert that into that sort of transpose. And we'll talk about that a little bit too. And you generally want to standardize your data. That plays a role. We'll see that in our example, because you want your model to like have as less noise as possible, because your model doesn't understand if something's just like doesn't make sense to it. And if someone comes to you and tells you like, I have a stock, it's going to have like 400,000% return in a week, you're going to be like, you're nuts. But the model does not understand that, and you have to make sure you're not feeding that stuff. And standardizing your data is generally important. And the dimensionality, I'm not going to get into it much, but it all falls into that category. You want to have a winning rate. Like the information you've been put into the model has a cost of processing. It will also have a cost of like making your model more likely to overfit. So you want to toss out the noise as much as you can. If you think some information is useless, just toss it out. If you think if you have too much dimensionality, there are algorithms out there that will reduce that for you, where you can just plug it in and use 2 lines of code to make your code, make your data cleaner. Now, with Python, there are generally 2 tools to handle your data, and that is the first thing you have to do whenever you're working a machine learning problem. And I would recommend using pandas, but you can also use NumPy as well. And I would even recommend using pandas to anyone who uses Excel. It's just a better Excel, completely better Excel. And you can handle your data with that pandas. And I've put in a couple of code blocks in case you want to go back to it in the future. For example, if you're using pandas, you can read an Excel file with just this simple function, and you can replace the missing values with medians just with this simple function. And you can scale your data with this using a scikit library.
Does the pandas have to read a CSV file, or can it do different like Excel
It can
formats,
read anything.
text?
Okay.
Okay.
CSV is actually you can open in Excel.
Yeah.
So that's you can, I think it's interchangeable. You can do
I mean,
that.
you can read. You can even read Stata works. I recently tried that. Like, I didn't have any Stata on my local. I was like, okay, pandas read Stata files. It's very popular and useful. That's why like people really love this
Got it.
because it's simple. It doesn't work if your data gets too large because like it's not the most efficient. But like as long as your data is not too large, it is perfect for handling the data, at least the initial data. And I'll go through the code and we'll look at it of how it works. So to wrap this up, like if you're looking at a machine learning problem, if you're trying to predict markets, predict credit defaults or whatever, the main 4 steps that you have to take is like the first thing you have to do is like know your data, what data you're going to need, and collect that data. And if that data is ready, look at it, pre-process it, understand it, because that's what you have to work with. And the second step, you will explore different algorithms and models, and you will conduct some experiments. You will see, okay, does SVM with these features work on this, or should we do neural networks, or should we go some other algorithm? And you will experiment with these, and you try to like find the best model you can. Okay, it seems that an RBF kernel or a polynomial or this design of a neural network with ResNet works best with this. And after doing all this, you need to validate your model. And the validation part is generally the idea that like you need to have a piece of unseen data in the end. After all the optimization, after playing with all your features, after like adjusting the Cs, adjusting the kernels, adjusting the design, after all that, you still need to leave another sample there. And you have to test it on that sample and to see if it works or not. Because if it doesn't work on that, you've just overfitted it on the whatever else you were doing then. Questions? Okay. All right, let's go look at a code. I'm gonna send you a couple of links. First, do you all have Gmails? I assume yes. Okay. So could you please go into Google Colab? Just could you Google that and open up a script? Right, were you able to open up Google Colab? You can also use this link, save this link somewhere, and I'll email it to you later on too. This is like have this script as like your sort of source code for future stuff, and you can all view it here, and I'll share it with you later on.
I haven't found it yet. I don't know if anybody else had an issue.
Could you click on the link I sent?
I'll just do that now.
Oh, I think I just sent it to Hugh. Huh. Okay, there we go. All right. I've sent you 2 links, and I want you to open them both up.
That worked. Thanks.
All right. Anyone else? Have you all opened it? Okay. All right. Now, this is called a UCI repository. It's generally like an open source database, and they provide data on like everything basically. It's not finance related, but it's like a simple data set that you can train and model on and have some intuition of how the whole process works. As I've said before, and I want to like try and model train a machine learning model on this entire data set, right? Now, if we look at the data, we have 4 classes. These, what are these? What do we refer to them? Are these X's or Y's?
Are those the X's?
These are the class values. The classes generally like the classes, labels, Y, they use them interchangeably. And the class information is that a car is unacceptable, acceptable, good, very good. We're trying to evaluate car quality here.
So that's
we
the
have-
result. So that'd be like the Y. Is that
Yeah,
correct?
yeah. These are the
Okay.
Ys. Like we know, like, okay, the car is good or bad. And we want to train a model that is able to find the best car based on these features. We have like 6 features here, and it like describes these features. Like this is the car acceptability, and our features are like the price, the buying price, the maintenance price, the comfort level, the number of doors, the people capacity, the lug boot size, the luggage boot size, and the safety of the car. And we want to train a model that is able to predict the acceptability of a car. I think this was in a like an exam or something. I'm not sure, like one of these tests they do on cars. But you want to predict this thing based on these features. Now, let's go to our Google Colab script. You should all have access to this and see this. But not, for now, look at my screen. I'll make sure to send this to you later as well. So this part is generally you want to import a bunch of libraries and you add this as you go along. Like don't look, you do not need to do this, but like each of the, like this is the way Python works. You import a library, you use the functions in that library to do what you're seeking to do. For example, I said like we're going to use pandas to read our Excel file, right? The data that they provided on that website. So I put this in. The rest of the stuff I've added as I go along. For now, ignore it. So I want to read the data. Fortunately, this website provides an API, which I can get from here. So I will give it the column names that I've seen on the data set here. Like as it is giving me the column names, right? And I will define a data frame. That's what the df is, just a variable. And I will feed that data set into this data frame so I can like work with it. Now I have it in a Python framework. And I go and read the data. And this is the data that I'm looking at. It's like 1,728 rows, 7 columns. This is our label or class, which is like this. We have safety, lug boot, persons, doors, maintenance, and buying, which is the price, I think, right? We have these ones. So these ones are the features, and this is the class we're trying to classify here. Just as simple as that. Now, I said before, we need to sort of convert these non-numerical values because the machine will not understand this. We need to work with this. So there's this function called mapping in pandas. And what it does is you can tell it, define it like a buying mapping right here, like very high equals to 4, high equals to 3, medium equals to 2, low equals to 1, and tell it to like, this is how you select a column with a name, like df under the brackets buying, and equals df under the bracket buying dot map buying underline mapping. So again, like whenever we're talking these codings, even like at this day, when I want to like map, I just go to Google Pandas mapping function. It's like if you're fresh, it's like, I don't know, like learning a new language or something. It's like whenever you don't have practice, you're gonna forget the actual commands, and that is fine because every one of this, it can be found on the internet. And I use the same thing for the rest of my features. I have a bunch of features and they all have a sort of a rational relationship with each other. Like small is smaller than medium, medium smaller than big. So I'm gonna just assign them like values from like 1 to 4, 1 to 4. And I'm gonna map this like that.
Those are your preferences. So when you're doing it, those are, maybe somebody likes a small boot, so, it could be the opposite.
And you just map those values and you do the same thing for your label. So like very good is better than unacceptable. So the way I did it from like 0, 1, 2, 3. We have 4 labels, right? I defined 4 like 0, 1, 2, 3. And let me actually cut this from here so you can see what happens to the data. Okay, so let's run this bit. Did it run? I think so. Yep. Now, after we run this bit, let's print this thing out. See, now if we look at the data, there's none of that like letters here. It's just all numbers. And this is something we can work with, right? And again, here, I'm going to define my X and Y, again, using pandas. Don't worry too much about the actual like functions I'm using. Like follow the logic with me because you'll have access to this. You go look at it. So I'm defining my X, which is like my first 6 columns, basically. That is my X. That's the X that I want to be able to predict the label based on. And I'm defining my Y as the last column here, the labels, the car acceptability or quality, as we will call it. And we will run this. So now we have an X and Y, right? If we want to like take a look under the hood, which is always sort of recommended. Like if I print Y here, you can see like it will give me the area of that. If I print X here, I can see like these are my X's. And that's exactly what I want. Now, as I've said before, we want to be able to create a testing sample and a training sample. And this is what this does. And for this, I import a library called the scikit-learn train test split. Like you see, like everything you want to do, there's generally someone who's done something that you can use it. So like from scikit-learn, we import this train test split. And with no fuss, we're able to like split our data set with just 1 line of code. And what this line does is just like it will dedicate 30% of our data set, which was like 1,700 something, to test samples. And it will select them randomly. Yeah. And the last thing we do here, I will scale the data. And the scaling the data, I just want to show you through an experiment, like what it would mean to scale the data. Because I'm going to train the machine learning model with both scaling the data and not scaling the data. Now let's do that. This is a logistic regression. This wouldn't teach that. I'm going to move past that. So any questions till now? Okay, good. But even like on seeing, as you see, logistic regression coding part of it is easy, but like we didn't go over the theory. Like for example, here, I'm training a logistic regression without scaling the data. And like I think I'm training the logistic regression this time with scaling the data. If I don't scale the data, I even see I receive an error, failed to converge. So generally good sense. Now let's go to the SVM here, right? Now I'm gonna do the SVM here again. We can see that like the SVM really doesn't work with this either. Like it does an 84% accuracy. And as I said, like similar to the ones we did before, like SVM equals to like a definition, kernel, RBF, gamma, random state. And don't pay attention to this. This is just like me measuring the time. That doesn't really matter here. And I will fit that SVM model to like our X and Y's. And for the accuracy part of it, I just predict a Y-pred in my test sample based on the X's. And I will compare the Y-pred to the actual, to the actual true value that I know is there. Okay, yeah, I knew something was wrong. Right. So here we can see that like the SVM actually did perform it. I realized I actually put the logistic in there. But the general idea, does anyone have any questions about how we drive the Y prediction and the like how we fit the X's and Y's?
So just doesn't want to make sure I'm reading this correctly. So the training got an 84%, but the actual got a 97%. Is that correct?
Yes, that is correct.
Okay.
But hold on. No, that is my mistake again. See, like I've put in the logistic regression in the print, and you're gonna face these sort of issues in your code as well. You're gonna go somewhere, it's not gonna make sense, and you're gonna have to print it. Let's run this again. Okay, now that makes sense. Right. Yeah, we have like a 100% accuracy on our train sample, like a 97 on our test sample, and this is favorable. This is like the best model we can do, generally speaking, right? And I actually like called the logistic regression function here. Does this make sense to you? Like how we define the sort of the Y prediction?
Yeah, that makes sense.
Okay, yeah, because like we train a model on this data. I'm repeating myself again. Like we fit the SVM model into the like training data, and there's a function called like predict. We do a svm.predict with the X test on the test sample, and we predict a bunch of Y's depending on the X's. The good thing is we know the true Y's on the test sample. We have that, so we compare the true Y's with our predicted Y's, and that will give us an accuracy. You would have a similar approach with the like R-square or whatever other measure you have. Right. So this will be our neural networks model, and as you can see, the whole thing is a little bit more complicated, but not that much. It's the exact same code you have in our slides. So we want to generally just define 3-layer with 1 hidden layer, and we have an optimizer here, as we mentioned in class, and we defined our loss function here, and our metrics is accuracy here. And this is
one thing you guys got to realize what Faraz is doing. You know, he hasn't written this codes. He's just giving you a sequence. And once you get the sequence, the cooked codes are available somewhere else.
Yeah, I mean, this is just like, because that's what I do in my own coding. I like at this point I have enough codes written like in history where I like whenever I get stuck on a function, I go back and look at it and be like, okay, what was that function? How do we do that? Because that's not the main point of this. I want you to be able to like generate knowledge out of a data set. The coding part is just something to be done. Now, as you can see, like whenever we train a neural networks model, the whole like process looks a bit different. And those are the whole concept of the epochs stuff that we were talking about. As you can see, we gave it a batch size of 32 here. And we also gave it 20 epochs, if I'm not mistaken. So 20 epochs here, right? And so the model you can see here, it will go over the first epoch, and you can see the batches here too, like these are different batches. And in the first epoch, it will calculate a loss function, and the accuracy is back, and you can plot all these, right? In the second epoch, it improves that loss function, it reduces it, the accuracy improves, and it will continue to do that going on, right? So like you generally want this to go down. Whenever like you stuck somewhere, you know, like that model's finished. Like you don't want the loss function to remain constant there. And have in mind that like I'm using TensorFlow and Keras to develop these functions. So as I said before, the functions are simple enough, but like whenever you need to import 2 main libraries for this thing. This is the first one, import TensorFlow STF, and you need to import these things from Keras. And again, like this might seem a little bit too complex, but if you just like Google Keras like model, TensorFlow models, it will just give you the libraries that you need to import. And I will share this code with you. I just want to go through the logic of how the whole thing works. All right, so like if you want to take a look at our, like the model we built, the neural network one, you can see the type, like we have an input space, it has the 8 things that we talked about, and it has a 4 output. And as I've mentioned before, always have an activation function of softmax when in your last layer, whenever you're classifying, because this will give me a probability of the car quality. What is the probability that the car quality is like highly acceptable? That's what this will give you.
Real quick, you just had the learn rate as 0.09 up there. How do you determine that it's or should be 0.09?
Trial and error. I think I was sort of experimenting with a bunch of stuff, but you don't really have to do anything. Let me just do this here. Like those are questions that you need to answer, right? But that's dependent on your specific application, right? I can't tell you like always use Atom Optimizer with the like learning rate of like 0.3.
So
you have to do it by iteration. You start
Yeah.
slow, and then
Yeah,
you overestimate, then you go back.
There are literatures depending on your problems that you could go read. I'm not familiar with all of them. Like for example, let's try and let's see what the effect of that was. You see, like my model, like performance dropped from 95% to 72%.
Yeah. So you're plugging in a learn rate to get that accuracy as high as, or
Yeah.
good spot. Okay.
Yeah, and so like the model was like doing bad stuff, like it's getting stuck if I don't give it that learning rate, right? But if I put a like initial, and I'm still losing the optimizer, right? But I'm just giving it an initial value to start with. I think it was 0.9, right?
Yeah, it was 0.9.
Yeah. And again, one thing you're going to face with neural networks is that like your outputs value are going to be different from time to time. Anyone knows why that is? Like your accuracy is going to be different each time you train the model.
Because
You're
each
pulling
iteration, the
different-
model is learning.
You're pulling different samples in each one of these epochs, right?
Yeah. Do you remember like when I said the initial weights are assigned randomly and it would start from a random place in a space and it will improve from there? That's why you'll get different results each time you train it. Now, there are ways to fix that. You can fix the spots whenever you're working on a project, like I do on like the projects I do. I'm like, okay, I don't want to deal with your stuff. I want to be able to objectively compare my stuff. So always start from this point. And that's how like what we call a random seed. But anyway, that's besides the point. And this is how you can always plot your stuff too. Again, it's a function. Like I did not know this function. I Googled plot neural networks using Keras TensorFlow and it gave me this function. And this way I'm able to like plot the neural network I designed, right? We have our input layer, this is our hidden layer, and this is our output layer. Exactly like the chart we saw in the slides. Now I'm gonna do neural networks without the scaled ones here too. And I've tried like a bunch of different neural networks with different optimizers and such to like see which one would work best. But the general idea of the code was the same. And with that, I think this concludes my time in lecture. Any questions?
I know it's been a complex kind of absorbing,
Yeah,
the drinking from the hydrant, but the story is